Okay,
Not sure if
great.
it's recording, not recording.
Oh, no, it's recording. All right. What's up? Share screen. Put on a nice shirt. Full share screen. All right. So, yeah. Hello, welcome. Thanks for coming, guys. My name is Fumi Shiru. I'm on the SAC team and junior SAC developer. And during the Jumpstart program, which is open to new hires and stuff, my team worked on a cryo-CMOS design verification with qubits project that was assigned to us by our sponsor, Rajiv, and conceptualized by Joseph Glick and with the help of Sedipta. Yeah, so today I would just like to give a brief overview of the project experience and then dive more into how it relates to system assurance and whatnot. So let's start with just acknowledgements. So the package was developed corely by the Jumpstart team, Abhishek, myself, Prayum, Ilhum, Henry, as well as Nick and Samantha. But after Jumpstart, they decided to drop from the team, but still a huge help in this process. Our mentors and subject matter experts, the person who sponsored this project was Rajiv Joshi, and it was the idea came from Joseph Glick. And Sedipto is a cryo-CMOS design engineer that helped us through the process in understanding what he would need best from a cadence side. We also got help from two Qiskit team members or leads, Daniel Paluzzi, who developed Qiskit Dynamics, and one of the developers from Qiskit Experiments, Will Shanks, who was a huge help in just getting up to speed on a lot of the core Qiskit use functionality. And then also a huge shout out to the SAC team, Abel, Tom, John, and Dennis, as I showed them my general overview of the process experience and got feedback, dived into how it could relate to SAC work, and got some good questions that helped me round out this presentation better. So we're going to start with just a general introduction, a Jumpstart project experience, just talk about that. And then afterwards, talk about just compute in general and how we can compare classical to quantum. And then afterwards, move into system assurance and quantum compute. I guess one thing to note is compute just meaning logical programmatic thinking that can be done with from any type of medium or architecture. So starting with the introduction. So our goal for this project was to aid in cryo-CMOS development with Qiskit-based methodologies that connects to cryo-CMOS circuit design to qubits. The package that is being built was built and tested was conceptualized by Joseph Joe Sedipto and grown out in 2024's IBM Jumpstart program, with ongoing developments that are still happening. So again, their team is looking for help. So if you're interested in this type of work, I'd be happy to share more information afterwards. So the goal was to leverage pre-existing Qiskit packages and technologies and tools to simply speed up the process that's being done for developing a cryo-CMOS waveform that can aid in quantum computing. Cool. And the viral package is just streamlining this research. So where does this cryo-CMOS arbitrary waveform generator even come into place? And how can we relate it to what we're used to in classical computing? Let's start with just general transistor logic in quantum. So I'm sure we're used to this. This is a transistor using voltage, and you can think of it like kind of like a switch where you turn the switch on, you see little electrons, and that lets you know it's a high voltage or a 1 value. And you turn the switch off and you see no electrons and it's like a 0 value. And here in quantum, we can kind of see it like a similar idea, but with a wave-like particle, where you send this kind of wave or particles through this double slit type gate, and then it interferes with the gate, and we get either a 1 or a 0 or something in between. In practice, it's actually done in the reverse order, where the qubit is staying stationary. This is the qubit over here. And the gate is the pulse we're sending and interfering or interacting with the qubit. and we'll send first the actual gate we want to use, like a Hadamard gate, and then get some weird interference pattern. But to read that data, we have to send another pulse, which is called a measurement pulse, that kind of translates this back into classical information. So what is the current scenario of bring up in development for a cryo CMOS chip? Well, there are 3 stages of level of detail similar to SAC, where you can first emulate the architecture so that the hardware engineer can get some quick feedback within an hour, or to a day, but the accuracy is not the best. You can use the current backends that are already developed and, be able to take that simulated waveform, but then you need someone like Alice or a calibration researcher who can manually take that and massage it into something that can be used on the qubits. And that can take up to 1 week to a month, depending on Alice's familiarity with Qiskit. And then finally, the best case is to use it on the actual architecture and you get accurate results, but then this would take 3 to 9 months of fabrication time. So the goal for Viral is to not like replace this process at all, but rather support this process by providing functionality that speeds up a lot of the actions that are already being taken, allows Bob to be able to do calibrations without really needing to talk to Alice, and allows Alice to experiment with different styles of calibration so that she can improve the calibration process used. And yeah, and Viral would help take this from like a 1 week to a month process to 5 minutes to a day, roughly, with the new bottleneck just being access to backend. Cool. So the Jumpstart project experience. This was like our final package and architecture at the end of the day, and it comes into an application, which are a set of like Python files with functions in them, and a tutorial notebook that goes through the steps the user would take from setting up and selecting a backend to importing their waveforms, calibrating those waveforms so they work as best as possible on that specific backend, and then recording and running experiments and verification tests, and finally saving the results. So we didn't start from there. Obviously, we started with just a tutorial called Calibrating Qubits in Qiskit. We just followed the tutorial documentation and created a Jupyter notebook. There was a proof of concept that you could take some simulated waveform and run it on real qubits. Then after that, we took that Jupyter notebook and created functions from it, and then organized those functions into specific sections like viral experiments, Hamiltonian, setup, waveform. And then finally, we reached a point where we realized Sadipto wouldn't like using this as is, and it wouldn't work with his current flow. So we try to make a terminal script that he can use so that he can stay in his normal developer environment and just call the script as needed. The impact of this was it helped with speed and accuracy. And the measurables we talked about before, but helped again with speed and accuracy of from a week long to a 5 minute long to a day process. Some challenges were cross-team collaboration, people's timing. Everyone was at different locations, people's knowledge bases. Yeah, some people were more experienced and had more important work to do at that time, while others were less experienced and a bit overwhelmed by the idea of quantum in general. And yeah, we just had to work through it. Another issue was mock and simulated backend compatibility. They were just trying to plug the inputs to outputs correctly, and there was a lot of detail involved with it. And getting access to real backend was a huge issue and slowed down progress because we couldn't really test it well, waiting in queues and stuff for our chance to run. And yeah, finally finding documentation and resources. And I actually found this to be very interesting because again, this is a quantum computer that's still currently being built and is almost at the stage of time-based computing with classical computer mainframes like about 50 plus years ago. So it just highlights the importance of documentation and how in these new fields and stuff, this information over time will need to be stored, recorded, and help others build upon it. And now we're at the stage of an alpha release where Sadipto would start using this package and put up GitHub issues, and then the team will start fixing those and adding more improvements to it. But yeah. And also an API to improve the user experience. So here's the actual package running, because yeah, let's just see what it does. So we first start by importing the viral package in. Sends us some good details. We import and set up our backend that we selected. Now we've imported our waveforms in that we want to calibrate for a specific type of gate instruction. And here we're running a general calibration process, which would allow someone like Sadipto to just kind of run that quick calibration process, but focus on the verification information. And here we're running the verification tests, with the first one being identified between the 0 and 1 state, the T1 experiment, which is the coherence time, the Ramsey experiment, which is similar to the T1, but now taking advantage of superposition, and the T2 Hahn. I don't understand that too well, but it was also very helpful, and dynamic decoupling as well. So once these run, we just save the data and record it for a physicist to analyze later and decide how well that did, and then collaborate with Sadipto to decide, okay, what needs to be done next. So that's just the general verification process for a gate level instruction. And while we haven't talked about it, I think it's good to stop here and just kind of see the process we have here. We have a cryo CMOS chip. It generates a pulse that acts like a gate, and it runs on hardware. And this hardware can be abstractified to represent a block sphere qubit. This qubit has two normal states we're used to, a 1 and a 0, and it also has access to superposition states, like a 1 and a 0 at the same time. These states are represented as a plus state, where it's 1 plus 0, and a minus state, 1 minus 0. You can picture it like the arrow moving in the opposite direction. And it also has an imaginary plus state, an imaginary minus state, which is at a phase shift over here, but again, is just a forward and a back arrow. So again, we can think of this like classical computing, where there's a 1 and a 0, just at different axes on the same qubit. And here's just a classical NOT gate you can think of, where this pulse represents a NOT gate, which would be called a poly X gate, and does the same logic that we would expect. Turns a 0 to a 1, or turns a 1 to a 0. So what are these verification tests that we run? And here I got some help from Abel, and I think a great thing to do here is remember the verification is verifying the behavior of that specific instruction. So here we ran an X gate, where in one case we didn't turn the X gate on. We didn't use the pulse to flip the qubit, so it remained in the 0 state. And then we did use the pulse to flip the qubit, and it turned to the 1 state. But as you can see, these clusters have errors in them, where there's some blue within the region and there's some red within this region, and they're not even very well separated. So when thinking about that and verifying, the best we could possibly say is what was the percentage error, and was it within the range of acceptable error for a 1 gate, and what was the acceptable error for a 0 gate, and verifying in that way. Another test was the standard and interleaved randomized benchmarking, where you kind of just stack the gate on top of itself a lot of times until the noise level is reached the point that it's just giving no information whatsoever. So you just kind of stack the gate a lot of times and see how noisy it gets over time, just to see the rate of change. Then we have the T1 experiment, which is the coherence time. So when we flip a qubit to the 1 state, it will naturally relax back to the 0 state again. And this shows how much time that happens within. And it's about, for at least this example, approximately 600, I think, milliseconds or nanoseconds, 1 or 2, something like that. And then we also have the T2 Hahn state, T2 Hahn experiment, which does the same thing, but for the plus to the minus state. And we see the same sort of behavior and rate of change. So we have this pulse, and we'd like to run it on a backend, but we also would like to get an ideal scenario similar to where you have a simulated version of expected values, and then you have the actual real thing. And here we use a Hamiltonian to do that, where a Hamiltonian describes the energy of the qubit in the system. Cool. And this is from Qiskit dynamics. And we just kind of call it in from Qiskit dynamics, and it does that for us. So there are other types of backends, as I mentioned. There's a mock backend as well as a real backend, which we're familiar with, and a simulated backend, like as the Hamiltonian. And these different backends allow us to do different types of comparisons and understand the noise from different perspectives. Where, yeah, a simulated versus fake shows what the effect of the pulse distortion in the presence of non-unitary noises. A fake versus real, you can ask what the effect of non-unitary noises, and a simulated versus real, you can ask how a non-unitary noise and pulse distortion works in practice. A lot of this doesn't mean much to me, but it does show the benefit of comparing these backends. So that was the viral package and what it does and why it was helpful to that specific team. But there was a lot of similarities between classical computing and the bring up process we do and quantum computing and the bring up process they do, where again, we have this idea of a transistor. And now it's important to note at the lowest level, instruction behavior can be described as a set of gates resulting in a 0 or a 1 state. So we have some sort of building block to build off of where we can at least know we verified the single gate that can act in a logical 0 or 1 state, or provide a logical 0 or 1 state. And we have this bring up process where people are trying to develop this distributed system, and there's a lot of things that need a lot of R&D that needs to happen, and different stages of accuracy in the process. And we also have this compute that seems to be parallel in some aspects to classical computing, where we have a NOT gate and a poly X gate. Cool. And then we have different zeros and ones at different axes. So system assurance and quantum compute. We've kind of just talked and focused on the lowest level that was done for the project, but we can build off of this. And at this point, again, a lot of this is an open area of research. And to the SAC team, I really encourage you guys to just ask the question of how could we verify at the next level as we move forward? Just knowing that, okay, we can verify a single gate, like an X gate. So let's move to the next level, gates to assembly instructions, where assembly instructions are made up of smaller gates that do generalized actions. Here we have Grover's search algorithm, which is a famous algorithm for searching through an unsorted array to find a specific value. A very high-level rough explanation of what's going on here is it's using a Hadamard gate to put the qubits in superposition, almost like show all the possible states. Then it uses an oracle to filter and say, I'm looking for this specific state, and flip it on its phase axes. And then finally, we have a diffuser that says, okay, now clean up the mess and give us just the state that we wanted at the end, like after we've kind of gone from a superposition state back to a classical and cleaned up the phase shifts done by the Z gate. And yeah, the oracles work. But yeah, again, I don't understand the details of this, but this is the benefit of assembly instructions, is you can abstractify to the next level where we have an initializer, an oracle, and something that gives us the average best value. And yeah, these are usually in practice called U gates, where they do an arbitrary U rotation in some way that's been described by these smaller gates. Cool. And here's an example of this, where we have an AND gate, where we have an A, B, and then we take a control TOEFL, which is 2 control gates, and then do some process to get the A plus B result back. And this is made up of a TOEFL gate and a control NOT gate, where it's like the top one is saying if A is 1, then flip B, and if A and B is 1, then flip the 0 qubit over here. So it's kind of like an if statement, but in quantum. And then finally, that's abstractified to the function level. And here I reach out to Dennis, and he also had a challenging question that was really helpful in building this out more. That SAC, if you think about it from a C++ like perspective, you take the C++ code that does something, you compile it down to object code, and then you give that object code to SAC and then it verifies whether that object code does what it's expected to do. And to do that, you need memory. And that's a very open area of research in quantum. Here are just some general things about memory. As you can see from the add instruction, each qubit almost represents its own little block of memory, where you have a register, ansel, and then a memory qubit that probably stores the result. Then here on the side, we have a short, high-level description of what quantum RAM could look like, where you have this function, and it has stages to it. Oh, apologies. Where you have first the control gate, then another control gate, and then the result from doing that. So we'll give it an input of 0 at that control gate. Well, we know that 0 won't activate any flips on a control gate, so it just stops there. Then we give it an input of 1. It will activate that control gate, flip it, and then store our result over there. And then later on, we can just grab that result later because it's been stored. And now in quantum, you can take advantage of superposition to say, let's put it in both the 0 and the 1 state by using the plus state. And that will take both paths and store both results in theory, so that you can quickly just collect all the results or one of the results as needed. Yeah. And that's kind of all of it. And yeah, it was just generally from the project side, we developed this package. I learned how to use Qiskit to make code and things like that. And it wasn't magic. It was like normal, start with a general tutorial, create like blocks of functionalities and build those functionalities and organize them based off of the classes that make the most sense. And then next, the impact. Now, this is a big question in quantum is like, oh, quantum advantage, what is the benefit of using it? And sometimes the benefit is just speed and accuracy. Like you don't need to create a new algorithm to do something, but just take advantage of the functionality that is there and automate some processes. So if there's something you've been thinking about automating that requires some quantum effects to see or something, or there's some algorithm you saw and you're like, oh, how do I make this easier to use? Follow the steps, create functions from it, and then, yeah, build out the package as needed. And then finally, yeah, project challenges. It is a cross-disciplinary area of research. There's so much open area of work that needs to be done, and especially highlighting system assurance, especially on a very sensitive quantum computer, system assurance is super important because you can't, like, the whole idea is we currently have NISQ, noisy, intermediate, quantum intermediate small-scale quantum computers, but we want to move to fault-tolerant quantum computing. And that requires system assurance that we know what went wrong, why it went wrong, and we can validate the information we're getting back. And if not, at least trace it back and fix what needs to be fixed along the way. And yeah, thanks for listening. Thanks for the help, especially with this. And like, just, yeah, I really encourage the idea of seeing classical and quantum computing. It's just compute that needs to be computed. Thank you. Yeah. Great. Any questions or? Oh, for sure. Yeah. All right. I found this slide to be the most helpful if you guys are looking for just thing, because it really does just kind of summarize the whole idea of it. But yeah, and let me stop sharing and stop recording. But thanks, guys. Yeah.